In the early 1960s, the United States was gripped by a humiliating, high-stakes Cold War panic. The Soviet Union was completely dominating the skies. They had launched the first artificial satellite, sent the first living creature into orbit, and placed the first human being into space. America, the world's undisputed industrial superpower, was lagging behind, watching helplessly as Soviet rockets chalked up victory after victory. Desperate to reverse the tide of history, President John F. Kennedy stood before Congress in May 1961 and issued a breathtaking, almost delusional promise. America would land a man on the moon and return him safely to the Earth before the decade was out. To the elite scientific establishment, the president's pledge sounded like absolute science fiction. At the time, American rocketry was in utter chaos. U.S. military missiles were constantly shaking themselves to pieces, exploding on launch pads, or veering wildly off course into the Atlantic Ocean. Top aeronautical minds at prestigious universities and military labs calculated the raw physics required to escape Earth's gravity with a crew, life support, a lunar landing craft, and enough fuel to return home. Their mathematical conclusions were unanimous. To launch a spacecraft heavy enough to land on the moon and blast back off, you would need a rocket so impossibly massive that it defied the fundamental laws of engineering. Yet 8 years later, on July 16, 1969, a towering 363-foot silver Titan known as the Saturn V roared to life at Cape Kennedy, hurling the Apollo 11 astronauts toward the cosmos. The driving force behind that unbelievable machine was Wernher von Braun. Von Braun was a complex, highly controversial German aerospace engineer who had built terror weapons during World War II before being brought to America under Operation Paperclip. But controversial history aside, when it came to rocketry, von Braun operated on a level of physical intuition that no one else on Earth could match. While American engineers were staring at traditional blueprints, trapped by incremental military missile designs, Wernher von Braun saw something entirely different. He saw a radical, counterintuitive truth about mass, momentum, and scale that everyone else was completely blind to. So, what did Wernher von Braun see that took us to the moon? He realized that to conquer space, you cannot build a ship that fights gravity with brute structural strength. You must build a machine that continuously destroys itself as it climbs. To understand why American engineers were failing in the early days of the space race, you first have to understand the brutal, unforgiving wall of physics known as Tsiolkovsky's rocket equation. A rocket is essentially a flying liquid fuel tank. To lift a heavy metal payload, like a capsule containing 3 astronauts into space, you need energy. To get energy, you need fuel. But fuel itself is extremely heavy. So if you add more fuel to push the spacecraft higher, you drastically increase the rocket's overall weight. Because the rocket is now heavier, you need even more fuel just to lift the new fuel you just added. This is the tyranny of the rocket equation. As your spacecraft gets bigger, the amount of propellant required increases exponentially, until over 90% of your rocket's total weight on the launch pad is nothing but liquid fuel. American engineers in the 1950s tried to solve this problem by treating rockets like stretched-out artillery shells or high-altitude airplanes. They tried to build sleek, single-unit structures out of thick, heavy steel to protect the engines and fuel tanks from collapsing under pressure. They were obsessed with structural integrity. They believed that a rocket had to be a solid, unified, ultra-sturdy ship that carried all its equipment from the launch pad straight to its destination. When these heavy, rigid American missiles were loaded with liquid propellant, the sheer weight was crushing. When launched, their engines struggled against the air resistance and gravitational pull of Earth's lower atmosphere. They burned through oceans of fuel just to climb a few thousand feet, leaving them with almost no velocity left to achieve orbit, let alone break free of Earth to reach the moon. Wernher von Braun looked at these rigid steel towers and saw a fundamental design delusion. Von Braun understood that Earth's gravity is an unforgiving tax collector that charges you for every single pound of dead metal you carry into the sky. He realized that carrying an empty fuel tank or a burnt-out engine casing into space was an engineering crime. Once a section of your rocket has consumed its fuel, that metal structure is no longer an asset. It is useless, suffocating dead weight pulling you down toward Earth. While American military designers were trying to build stronger, heavier single-structure rockets, von Braun championed a concept that sounded horrifyingly wasteful to traditional engineers: staging and deliberate self-destruction. Von Braun envisioned a rocket that wasn't a single ship at all, but rather 3 separate, distinct rockets stacked on top of each other in a vertical tower. As the massive first stage burned through its mountain of fuel, it would hurl the ship through the thickest, hardest part of Earth's atmosphere. The second the fuel ran dry, the entire bottom section, the giant engines, the massive metal tanks, the heavy plumbing, would be violently blown away with explosive bolts and dropped straight into the ocean. Suddenly, the remaining upper portion of the rocket would become immensely lighter. The second stage engines would ignite in thin air, pushing a drastically lighter vehicle to hypersonic speeds. Once its fuel was exhausted, it too would be ripped away and discarded, leaving a tiny, nimble third stage to fire its engine and fling the astronauts toward the moon. To traditional engineers, discarding millions of dollars worth of precision machinery into the Atlantic Ocean seconds after launch seemed absurd. But von Braun saw that throwing away 95% of your rocket along the way was the only mathematical key to reaching the heavens. However, designing a 3-stage rocket on paper was one thing. Building a machine capable of carrying out that math was a completely different nightmare. When von Braun presented his master concept for the Saturn V, American engineers were horrified by the sheer scale of what he was proposing. To lift the Apollo spacecraft out of Earth's gravitational clutch, von Braun calculated that the first stage of the Saturn V needed to produce a mind-boggling 7.5 million pounds of thrust. 7.5 million pounds of thrust was more power than all the hydroelectric dams in the entire United States combined. It was enough energy to light up the entire city of New York for a night. No engine in human history had ever been built on that scale. When American propulsion experts tried to scale up conventional rocket engines to create the legendary F-1 engine for the Saturn V, they hit a chaotic, explosive wall known as combustion instability. Inside a massive rocket engine, liquid kerosene and liquid oxygen are pumped into a burning combustion chamber at terrifying speeds. When you try to burn hundreds of gallons of fuel per second inside a confined metal chamber, the fire doesn't burn smoothly. It creates violent shock waves of pressure that bounce off the chamber walls. In early tests of the F-1 engine, these invisible pressure waves created acoustic tornadoes inside the engine. The sound waves were so violent that they swirled around the chamber like invisible sledgehammers, tearing steel walls apart and causing giant test engines to explode into fireball fragments within milliseconds. Mainstream American engineers threw up their hands. They argued that an engine of that size was physically impossible to stabilize. They urged NASA to abandon von Braun's giant single-engine cluster concept and instead build dozens of smaller, safer engines strapped together, a setup that would have added catastrophic mechanical complexity and weight. Once again, von Braun saw what everyone else missed. He realized that you couldn't stop the violent shock waves inside the fire chamber with thicker metal walls or softer fuel pumps. You had to master the fluid dynamics of the explosion itself. Von Braun and his team designed a revolutionary raised copper grid called a baffle on the face of the fuel injector plate inside the F-1 engine. These copper baffles acted as physical acoustic dams. When the chaotic pressure waves tried to swirl around the burning chamber, they slammed into the copper walls and were immediately broken apart before they could build up enough resonant energy to destroy the engine. Von Braun didn't try to eliminate the violence inside the engine. He redirected it, turning a catastrophic explosion into a steady, controlled, roaring pillar of fire. Each of the 5 F-1 engines on the Saturn V first stage pumped 3 tons of fuel every single second. The turbopumps driving the fuel were so powerful that their internal spinning turbines generated 55,000 horsepower, the equivalent of dozens of steam locomotives packed into a space no bigger than a trash can. Yet, von Braun's vision went even deeper than the raw horsepower of the engines. He saw a fatal blind spot in how American engineers approached the guidance and steering of rockets over immense distances. In early American space concepts, rockets were steered using simple mechanical rudders placed in the flaming exhaust stream, or by relying on radio signals beamed from ground radar stations on Earth. Von Braun knew that radio signals from Earth were far too slow, vulnerable to atmospheric interference, and useless once a rocket went behind the moon. Furthermore, flaming exhaust rudders degraded under high heat, losing control authority as atmospheric pressure shifted. Von Braun realized that the rocket had to become an entirely self-contained, autonomous, intelligent organism. He engineered the instrument unit, a 3-foot-tall, ring-shaped brain mounted near the top of the Saturn V rocket. Inside this ring, far away from the heat and vibration of the engines, sat ultra-precise, fluid-suspended gyroscopes and accelerometers, linked to a digital computer. Instead of steering with external rudders, von Braun's system dynamically calculated the rocket's exact position in three-dimensional space hundreds of times a second. If a sudden high-altitude jet stream gust pushed the Saturn V off course, the instrument unit would instantly detect the microscopic drift and command giant hydraulic actuators to physically tilt, or gimbal, the massive main engines at the base of the rocket. The rocket didn't just push itself through the sky. It actively wiggled its massive burning tail to balance itself on a pillar of fire, keeping a 3,000-ton metal building perfectly poised on a needle-thin trajectory toward the moon. When the Saturn V finally stood on the launch pad in July 1969, it was a physical manifestation of von Braun's vision. A 3-stage monster burning through 15 tons of fuel per second, shedding its own body parts into the ocean, controlled by an internal guidance system that adjusted every microfraction of a second. When the 5 F-1 engines ignited on Apollo 11, the shock waves shook the ground for miles around, cracking soil and rattling windows across Florida. The sheer, terrifying power of the machine lit up the sky like a second sun. As the rocket climbed into the blue, the giant first stage burned out, detached, and tumbled into the sea. Minutes later, the second stage did the exact same thing. What was left, floating gently in the absolute silence of Earth's orbit, was not a massive, clunky iron tower, but a lightweight, pristine, perfectly targeted spacecraft carrying 3 men toward the lunar surface. Consider what would have happened if NASA had stuck to the original concepts of conventional American engineering. If they had built heavy, single-structure rockets or attempted to launch giant, non-staged ships using dozens of uncoordinated smaller engines, America would have suffered catastrophic launch after catastrophic launch throughout the 1960s. The decade would have ended, the Soviet Union would have won the moon race, and human space exploration might have stalled for a generation. We often remember the Apollo program as a story of courageous astronauts, starry-eyed dreamers, and political triumph. We picture Neil Armstrong stepping onto the dusty lunar surface and delivering his immortal words about a small step for man. But behind that small step was a gargantuan, terrifying machine that defied everything traditional engineering thought was possible. Wernher von Braun saw that reaching the moon was not about building a ship that could survive the journey intact. It was about having the cold, mathematical courage to build a flying mountain, ignite a controlled explosion capable of shaking the Earth, and discard 99% of your creation along the way, just to give 3 human beings the velocity they needed to touch another world.